Hi, I am Sundaraya, Assistant Professor, Department of Mathematics. Today we will discuss about the definition of the probability and some of the examples on probability, some theorems on probability. Now I am sharing the screen, whiteboard. Probability. Probability starts with random experiment. A random experiment is an experiment whose outcomes are all already known to us. That is called a random experiment. For example, random experiment. Random an experiment whose outcomes are already known to us and we don't know about which outcome is occurred at the point of time is called a random experiment. Example, tossing a coin. Tossing a coin. This is a random experiment because when we are tossing a coin, then we have two outcomes are there. Either a falling head on the top or falling tail on the top. Therefore, only two possible outcomes are there. The outcomes are already known to us. Therefore, that is a random experiment. Second one, throwing a die. Throwing a die. This is a random experiment because the set of all possible outcomes are getting one on the top of the die, getting two on the top of the die, etc. Getting a 6 on the top of the die. Third one, if we take a card from a well-shuffled pack, then that is a random experiment. Already we know the set of all elements, cards in the pack is known to us. Therefore, choose a card from a pack, well-shuffled pack. This is also random experiment. Therefore, a random experiment is an experiment whose outcomes are already known to us. And which outcome is occurred at the point of time we don't know. That is called a random experiment. Simply, all games are random experiments. And whose outcome is not known to us, that type of experiment. An experiment whose outcomes are, we don't know exactly. Those type of experiments are called non-random experiments. Non-random experiments means science experiments, laboratory experiments, These experiments are not random experiments. Now, what about an event? Suppose, let us choose an experiment which is random. The first one, tossing a coin. The set of all possible outcomes is called the sample space of the random experiment. tossing a coin, tossing a coin. This is random experiment. The set of all outcomes are falling tail on the top, falling head on the top. Therefore, this is called a sample space. Second one, throwing a die. This is random experiments. This is one, getting one on the top, getting two on the top, three on the top, etc. 6 on the top. Therefore, this is a random experiment. This is the sample space. Next one, event. Event. Let S be a sample space of a random experiment. Random experiment. If E is subset of S, then E is called an event. Outcome means non-divided event. In the events, there are several types of events are there. First one is mutually exclusive events. Mutually exclusive events. Let E1, E2 be two events. The events of a random experiment. If E1 intersection E2, E1 intersection E2 is equal to empty, then they are said to be mutually exclusive events. Next one, equally likely events. Equally likely events. Equally likely events means that if n of E1 is equal to n of E2, the number of favorable outcomes to the event E1 is equal to number of favorable outcomes to the event E2. Then we say that those events, E1 and E2, then E1 and E2 are equally likely events. Equally likely events. Example, throwing a die, what is the sample space? S is equal to getting 1, 2, 3, 4, 5, 6. Let E is the event of, E1 is the event of getting even number. E2 is an event of getting odd number. And E3 is the event of getting getting prime number. Prime number. Here observe that E1 is event of even number. That means 2, 4, 6. E2 is event of getting odd number 1, 3, 5. E3 is event of prime number. E3 is event of prime number. Prime number means 2, 3, 5. Therefore, here E1, E2, E3 are all equally likely events. E1 intersection E2, E1 intersection E2 is equal to empty. Therefore, mutually exclusive and equally likely events. E1, E2 are mutually exclusive and equally likely events. E1, comma E3 are not mutually exclusive because who is an outcome which is favorable to both E1 and E3. Therefore, those are not mutually exclusive, but equally likely events. Equally likely events. Now, how to define probability of an event in the sample space? The probability of an event in the sample space defined like this. Probability of an event. Let S be a sample space, E is an event of S. Then the probability of E, P of E is defined by N of E by N of S. N of E by N of S. That means number of favorable outcomes to the event E by total number of possible outcomes. Total number of possible outcomes. Therefore, this is called a probability of an event. Probability of event. In fact, probability is always greater than or equal to 0 because E is subset of S. Therefore, N of E is less than or equal to N of S. Therefore, probability is always greater than or equal to 0. Greater than or equal to 0. Therefore, the following conditions are satisfied. P of E is always greater than or equal to 0. Second one, P of E is always less than or equal to 1. Therefore, probability is always lies between 0 and 1. Third one, P of sample space is equal to 1 and P of empty set is equal to 0. Therefore, simply the probability of an event means that is always greater than or equal to 0, less than or equal to 1. And P of E is equal to N of E by N of S. N of E by N of S. Next, P of E bar. Suppose E is an event, E bar is the S minus C. E bar is the S minus C. then automatically we have P of E bar is equal to 1 minus P of E. 1 minus P of E. P of E bar is equal to 1 minus P of E. P of E is equal to 1 minus E. This is one property. And if E1 and E2 are mutually exclusive events, then we have P of E1 union E2 is equal to P of E1 plus P of E2. Before going to that one, we have a theorem that is probability addition theorem. Addition theorem on probability. Addition theorem on probability. Let E1 comma E2 be events of a sample space yes, then P of then P of E1 union E2 is equal to P of E1 plus P of E2 minus P of E1 intersection E2. Now, how to prove this one? How to prove this one? By using the definition, a classical definition of probability. Let us take E1, E2 be events of the sample space. According to the definition, P of E1 union E2 is equal to N of E1 union E2 by N of S. Number of favorable outcomes to the event E1 union E2 is by total number of possible outcomes. Total number of possible outcomes. Here observe that this is E1, this is E2. E1, this part, this is E1 intersection, E1 intersection, E2. Therefore, the number of elements in the E1 union E2 is equal to N of E1, number of elements in the E1, N of E2, number of elements in the E2, minus N of E1 intersection E2. Because in E1, one time E1 intersection E2 is calculated, number of elements in the E1 intersection E2. In the second time, in the E2, we have second time we added the number of elements in the E1 intersection E2. N of S. Therefore, that is equal to N of E1 by N of S, N of E2 by N of S minus N of E1 intersection E2 by N of S. Therefore, this is equal to P of E1, P of E2 minus P of E1 intersection E2. Therefore, this is called addition theorem on probability. And if note, if E1 comma E2 are usually exclusive events, then P of E1 union E2 is equal to P of E1 plus P of E2. Why? Because since P of E1 interaction E2 is equal to P of E empty, P of empty is equal to 0. Because E1, E2 are usually exclusive events. E1, E2 are usually exclusive events. Therefore, if E1, E2 are mutually exclusive events, then P of E1 union E2 is equal to P of E1 plus P of E2. Now, some of the examples on probability and addition theorem on probability. First problem number 1. Two dice are thrown. Two dice are thrown. What is the probability that the sum of the two numbers on the dice is 7? What is the probability that? What is the probability that the sum of the two numbers, the sum of the two numbers is 7. Therefore, how many dice are thrown? Two dice are thrown. Therefore, sample space S contains first die 1, second die 1, first die 1, second die 2, etc. 1, 6. Similarly, 2, 1, 2, 2, etc. 2, 6. Therefore, 6, 1, 6, 2, etc. 6, 6. Therefore, there are n of s is equal to 36. Let E is the event of the sum of the numbers on die is 7. Therefore, what are the favorable outcomes to the event E? Therefore, event E contains 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. Therefore, how many outcomes are there? There are 6 outcomes. Therefore, P of E is equal to N of E by N of S. That is 6 by 36. That is equal to 1 by 6. 1 by 6. Therefore, this is the probability of that one. Second one. A die is thrown. A die is thrown. What is the probability of? What is the probability of getting a number divisible by 3? Therefore, the sample space S is equal to 1, 2, 3, 4, 5, 6. Set of all possible outcomes. Event E is equal to getting a number divisible by 3. Therefore, there are two favorable outcomes are there, 3, 6. Therefore, N of E is equal to 2. Therefore, P of E is equal to N of E by N of S. 2 by 6 is equal to 1 by 3. Therefore, when we are calculating probability, we need a sample space and the event to be known to us. Event is what? Therefore, we have to choose the number of favorable outcomes to the event is by total number of outcomes. Now about addition theorem examples. A die is thrown. What is the probability of getting an even number or prime number? Even number or prime number. While we are throwing a die, what is the probability of getting a number which is even or prime? Even is equal to E1 is equal to even. Even is equal to what are the even numbers? 2, 4, 6. Prime E2 is equal to prime number. Prime numbers are 2, 3, 5. 2, 3, 5. And there is a common outcome is there, which is favorable to both E1 and E2. E1 intersection E2 is equal to singleton 2. Therefore, what is the probability of getting a number? Probability of getting a number which is even or prime. R prime. Therefore, we need the probability of E1 union E2. Therefore, according to the addition theorem, P of E1 plus P of E2 minus P of E1 intersection E2. N of E1 by N of S 3 by 6 plus 3 by 6 minus common outcome is only one outcome, which is favorable to both the even and prime, 5 by 6. Therefore, this is called one of the examples for the addition theorem. One of the examples for addition theorem. And another one is there are there are 1 to 25 numbers are there in 1 to 25 numbers are there in a box. if we choose or select a number at random, what is the probability of what is the probability of that number is divisible by 5 or 3. 5 or 3. Therefore, we need the addition theorem on the probability to doing this problem. Why? Because that number must be divisible by 5 or 3. Either divisible by 5 or divisible by 3. Therefore, R is there. Therefore, that is union. Therefore, we need even in. Let A be the event of a number which is divisible by 3. That means divisible by 3 means 3, 6, 9, 12, 15, 18, 21, 24. Therefore, there are 8 numbers are there. Therefore, n of A is equal to 8. B is an event of a getting a number which is divisible by 5. Therefore, this is 5, 10, 15, 20, 25. Therefore, n of B is equal to 5. N of B is equal to 5. Therefore, we need the P of A union B. According to the addition theorem, P of A plus P of B minus P of A intersection. Why we should take A and B? Either A or B. We need getting a number which is divisible by either 3 or 5. Therefore, we should calculate P of A union B here. P of A already P of A is equal to 8 numbers are there. 8 by total numbers 25. Sample space contains 25. P of B is 5 numbers are there. 5 by 25. There is only one common outcome is there, 15, which is divisible by both 3 and 5. This is 1 by 25. Therefore, 12 by 25. Therefore, this is addition theorem on probability. Addition theorem on probability. Now, what is the classical definition of probability? Classical definition of probability. P is a function from power set of all subsets of sample space S2 0 1 satisfying be a function such that first one probability of S is equal to 1. Second, already P of any subset of S is always lies between 0 and 1. That is clear in the function. If E1 intersection E2 is equal to empty, that implies P of E1 union E2 is equal to P of E1 plus P of E2. This is called a classical definition. Classical definition of property. A function which satisfies S is a sample space of a random experiment. Power set of S, set of all subsets of S, P of S. P is from P to S to 0, 1, be a function. That means every P of an event lies between 0 and 1, satisfying the following conditions. P of total sample space is equal to 1. This P of S is different from this P of S. This is power set of S. This is P of probability of S is equal to 1. If E1, E2 are mutually exclusive events, then P of E1 union E2 is equal to P of E1 plus P of E2. Then any function satisfying these conditions is called a probability distributive function. And this is the classical definition of probability. Classical definition of probability. Okay. This is a small theory about probability. And in this discussion, we discussed about what is the definition of the probability, how to calculate the probability, what is the addition theorem on probability, and how to use addition theorem on probability is discussed by us. Thank you for listening this one. Thank you.